All right, what's up, everybody? So I wanted to finish up this section here talking about something that's near and dear to my heart because it was what I worked on for my master's work, my master's thesis. And it's with your book edition being the second edition, it actually added in the Madden-Julian Oscillation. So I was really, really excited to see that. So I'm really just going to breeze through a lot of this information. It's going to be a lot, but don't worry, you're not going to have to know a whole like mess of things. But I just want to share with you some things about this lovely, starting to become more well-known oscillation on our planet. So this is the Madden-Julian Oscillation. So this is something, it's a planetary scale, so it's really, really huge. It's a 30 to 90 day oscillation of thunderstorms that moves slowly eastward. And this is the dominant mode of intraseasonal variability of rainfall in the tropics. And so there's 8 phases of this cycle. And so what we're looking at here in this graphic, and I know it's like there's a lot going on, there's like a lot of hatching and stuff, but basically the tip of India is right here on this line, and the Americas, like South America, is right here. So this would be basically looking at the central equatorial Pacific. So this is looking at the separate phases. So you can think of the dark shading here as enhanced cloudiness or thunderstorms. So you can see how in these different phases, how it's moving towards the right and bottom left of this figure. So it's basically this propagation or movement across the Pacific Ocean. And so we can look at this sort of oscillation very similar to how we do ENSO in that it has a strength. So basically, the stronger the MJO, the deeper the penetration of these thunderstorms into the upper atmosphere. And so what we see here, this is called the MJO phase diagram, and it indicates the different phases. And the line here is indicating the month and day in which the MJO is active. I can't remember what day this is for, or from February to January, sorry. And so this is from last year, sorry, from 2022. It's literally right here, duh. But it like shows like the further out that it is from the center of this circle, the stronger the MJO cycle. And the further in, like if it's in the middle of the circle, then it's kind of in a neutral phase and it's not as discernible as where it's at. So the structure of the MJO is really quite fascinating, honestly. So this image here is looking at the total column precipitable water. You can basically think of it as moisture. So like the red sections here are indicating more moist areas. And so these blue or the black arrows are indicating this westerly and easterly flow of active convection kind of coming together near the center here. And so ahead of this convection is a suppressed region at the equator. Notice how there's not as much like strong red colors here where this rightmost arrow is. And then we can also sometimes see these cyclonic vortices on either side of the equator. So think of like if you were to run your hand through water and see those little swirlies on either side, literally the same thing, but in the upper atmosphere and lower atmosphere too. It's really, really quite cool. It's a very, very fascinating sort of observation. And so even though this is a tropical oscillation, it produces what we call a Rossby wave train that modulates and modifies climate here in the extratropics or the middle latitudes. So a Rossby wave train is basically just this upper level pattern that we see, this kind of wavy sort of pattern of regions of high and low heights. It's a very well studied phenomenon. And basically this dark gray here is showing increased tropical convection and latent heat release. Remember, when we make clouds, we're releasing heat. And so this thunderstorm activity excites a wave train that then follows all the way up into the Pacific North America pattern. It's really freaking cool. And we've known about this since like 1981. It's the coolest thing. And this is once again just kind of looking at the structure of the MJO from sort of the previous slide, kind of just trying to indicate, and I did not make this image, it's a little bit shoddy for me, but it's all right, but just showing the cyclonic vortices at the surface and actually anticyclonic vortices up above, which is really interesting. within the convection, and then ahead of the convection, we would basically see the opposite. So anticyclonic motion at the surface and cyclonic motion up top. Really, really, really cool, I think. And just that same idea with this image again. So just the cyclonic vortices on either side, I just think is the coolest thing ever. So that was a very quick and dirty explanation of what the MJO is, put in 5 minutes, but that's okay if that was like way too much information for you. Remember, this is a video. You can pause it and rewind it if you so choose. But here's just our summary of what we have covered this chapter. It seems like a lot, it sure has been a lot, and we've breezed through it quite quickly. But we talked about the average atmosphere, right, which gave forth the 3-cell model, right, the Hadley, Farrell, and the polar cell. And then that gave rise to these larger scale circulations and why they can matter climatologically. So our west v east coast of the United States, our desert regions around the world, the monsoon cycle, and the ITCZ movement. And so meaning El Nino and La Nina, and then we just finish up with the MJO. So moving forward now into chapter 10, I want to just introduce some of these concepts that we're going to build onto upon my return. But I want to introduce them now so that they're not super new later. So we're going to start actually talking about the fun stuff, in my opinion, the fun stuff. And so with this, we have to start indicating air masses with descriptions and names. So we basically name air masses with where they've spent time, and meaning continental or maritime meaning water. So they spent time over land or they spent time over water. And then we indicate whether they're polar or tropical. Basically, are they warm or cold? Basically. So tropical would not necessarily mean like a dry region. Tropical is meaning like hot here. And then we have Arctic as well, meaning very, very cold and very, very dry. So the interactions of these different air masses is actually what brings us some really, really interesting weather phenomenon, and 2 of which hopefully we'll see before the end of the semester. One being lake effect snow. So this is continental polar air going over warm water. This image here is looking at Lake Michigan, going into the Michigan area, and the warmer colors here indicating the more intense snowfall for this region. So as the air travels over the water, it picks up moisture and releases all of that moisture over the landmass. And we can literally see greater snowfall totals right adjacent to the coastline. And here's a schematic version of what lake effect snow looks like. Then something that we see here in our neck of the woods is something called atmospheric rivers. So this is when maritime tropical water or maritime tropical air hits the coast, in our case of the west coast of the United States. This is a feature that we see all over the world, but it's very prominent for our weather and our climate here in California. So atmospheric rivers are defined as a narrow zone in the atmosphere that transports absolutely huge amounts of water vapor from the tropics to the mid-latitudes. So we're once again looking at a precipitable water image here. So you can literally see this ribbon basically extending from Hawaii all the way up here into California and depositing moisture here. This was actually from last October when we had a really spectacular event here. And here's a satellite image showing something similar. It's not from the same event, but it definitely is showing a lovely atmospheric river from the tropics to the west coast of the US. It literally looks like a river in the sky. It's really cool. So now we're going to also start talking about fronts and cold fronts and warm fronts, and what they mean and what they can bring forth. So the reason why I needed to start with talking about these air mass names is because when we talk about fronts, we're generally considering the type of air that's behind the front. So behind cold fronts, we tend to have continental polar air because it's cold, generally dry. And in warm fronts, what's behind the warm front tends to be this maritime tropical. So it can be warm and maybe dry or moist. So these different air masses interacting with each other is what can drive weather patterns all over the country and all over the world, really. So focusing on cold fronts first, cold fronts are fascinating. They are defined as cold air that is actively advancing into a region which was formerly occupied by warmer air. And on average, they tend to be twice as steep as warm fronts. So you notice how this is a pretty steep bulge here, because the friction at the surface is trying to slow down the air at the surface. These little buddies are trying to move through the party so fast, but the surface is like, whoa, hold it back, buddy, calm down. And they also advance about 50% faster than warm fronts. So we tend to see more violent nature of weather in comparison to warm fronts. So cold fronts tend to be associated with severe thunderstorms and supercells and tornadic activity, whereas warm fronts tend to be more associated with broad, just rain showers. And again, this is generally considering other parts of the world, not necessarily considering the Bay Area, because we don't get thunderstorms here that often. Warm fronts, again, going into this idea of warmer air invading the territory of formerly occupied cooler air. And again, because they have a much gentler slope, as we can see in this schematic here on the right, the cloud deck that results from frontal lifting, it can be much larger and have an extended period of light to moderate precipitation, as opposed to like these really intense thunderstorms that we would see ahead of a cold front, which is what this is trying to show here in this satellite image. And then this schematic here as well. So also just want to point out while we're here, notice this counterclockwise motion around the center of low pressure in the northern hemisphere. Couple other things: when warm fronts and cold fronts love each other so much they combine, and they are called an occluded front. It's usually when one of the fronts overtake another. It's more common for a cold front to overtake a warm front, again because they're moving faster. And generally the later stages of a storm's life cycle is when this is happening. And there are cold types of occluded fronts and warm types of occluded fronts. Don't you worry, I do have some, of course, maybe not so internet appropriate analogies to help us remember some of these things upon my return. So just a few more fronts and boundaries that I want to address before I end this video are that of stationary fronts. So that's when there's not really, when airflow is moving on either side, they're not really acting on each other. They're just kind of there. Like there's definitely distinctive cold and warm air boundaries, but they're not making each other move. Precipitation is still possible with stationary fronts, by the way. And then lastly, there's this idea of dry lines. So dry lines are these differences in air mass moisture with the temperature being relatively the same, where dry air is more dense than moist air, which is really quite crazy. And this is a really, really, really important aspect when we're looking for severe weather forecasting, because with dry air being more dense, it's moving things out of the way, which can trigger a lot of upward vertical motion and spin sometimes. And so that's when we can get these really intense supercells and tornadoes. And this is just an example of what a dry line can look like. So this is looking down in the southern US. So you have maritime tropical air trying to scoot north. You have continental tropical air trying to scoot northeast. And with this dry line here, and if you have a look at the temperatures versus the dew point temperatures, remember temperatures on top, dew points on the bottom, you can see that the air temperatures are relatively the same, but the dew points are wildly different. And this is like in a super extreme case. I don't think in my time of looking at weather maps, I'm not sure if I've seen dew points in the 80s. Not to say it can't happen, but it's not super common. But anyway, with this dry line, it's instead of being that blue or red and solid, either triangles or half circles, it's a orange line with not filled in semicircles. So that's just how we indicate them on surface maps. So upon my return, we will talk more at length about these and where they come into play in terms of mid-latitude cyclones. Thank you so much for watching, and I'll see y'all on the flippy floppy. Thank you.